покажем пример использования транскраниальной магнитной стимуляции для...
We're going to show you an example of how transcranial stimulation is used.
Для этого мы будем использовать аппарат с МРТ-навигацией. Здесь уже на экране вы видите индивидуальное МРТ нашего испытуемого. Я сейчас на Анастасию надену маркер, который позволит отслеживать нашей инфракрасной камере. Наверное, ее не видно сейчас в камере, покажем ее чуть позже. Положение головы испытуемого, и параллельно мы будем отслеживать положение стимулирующего корпуса. Скажите, вдруг некомфортно. Удобно? Теперь нам надо увидеть, что наша инфракрасная камера видит положение маркера. Ну, вроде как она даже видит. Сейчас мы будем указывать, мы поставили на индивидуальном МРТ испытуемого реперной точке, две точки в области ушей, одну точку на спинке носа, назиум последняя, и сейчас мы уже поставим уже на реальной голове испытуемого. Нажмите, пожалуйста, кто-нибудь эту левую педаль, когда я скажу, можно мне. Вот эту. Я когда скажу, тогда попробуйте. Спасибо. Просто Enter. Да. Отлично. Все. Теперь мы поставим дополнительные точки для регистрации головы испытуемого с указательным его МРТ. Так, верните, пожалуйста, это правильно. Не очень хочет видеть. Для того, чтобы картировать двигательную кору, мы должны будем поставить электромиограмму на мышцы. В данной ситуации мы хотим исследовать двигательную кору руки, поэтому мы поставим электромиограмму на мышцы руки. Будем использовать мышцу, отводящую большой палец, абдуктор полисис бревис, и мышцу, отводящую мизинец.
We're putting on this sticker.
Большой палец к мизинцу. И
you find that spot on your thumb, the bottom of your thumb. It's video number 2 actually.
Там видно, как мы ставим электроды, это мы поставим поверхностные биполярные электроды на мышцы кисти. Можно делать картирование, в принципе, любых мышц. Картируется даже диафрагма, мышцы гортани. Ну, в данной ситуации вот посмотрим на кисть. Мы поставили электроды. У нас один электрод земля и есть биполярные электроды на мышце, отводящий мизинец, и на мышцы абдуктор коллисный пресс. Все, теперь мы готовы к проведению ТМС-картирования. Перед началом стимуляции с помощью транскраниальной магнитной стимуляции, ТМС-стимуляции, мы обязаны дать нашему испытуемому беруши. Умеете с ними обращаться? Мы должны одеть наушники или беруши также сами. Так, мы дали нашему испытуемому беруши, надели сами беруши или наушники, я надела беруши, проверили еще раз, что у нас у испытуемого нет никаких монет, кредитных карточек, золотых слитков в карманах. Настя, нет, никакого металла нет. У меня, что я тоже не обвешана ключами, чем-то другим магнитным на всякий случай. Теперь мы готовы начинать. Начало картирования – это всегда так называемое грубое картирование. То есть сейчас мы попробуем сориентироваться на двигательном коле. Вот это конвекситальная поверхность полушарий, вот центральная борозда, вот прецентральная извилина, вот постцентральная извилина. Мы будем начинать картирование с вот этой области прецентральной извилины, которая называется моторная кнопка руки. Это область представленности репрезентации кисти. Где-то отсюда мы и будем начинать. Вот здесь визуализируется текущая электромиограмма. У нас сейчас развертка 200 микровольт. Ну, значит, шум у нас здесь где-то меньше 20 микровольт. Нам это достаточно. Хорошо, можем начинать. Мы показали, Анастасия уже знает это ощущение ТМС. Если бы Настя не знала, мы бы еще раз показали, как выглядит стимул, какой он может быть громкий. Сейчас я нажму, и вы услышите звук. Вот такой звук будет во время стимуляции и может двигаться рука. Непроизвольно, не пугайтесь. Если вдруг какое-то неприятное ощущение, обязательно говорите. Хорошо. У нас сразу, видите, большие ответы, больше 2000 милливольт. Значит, мы сразу уменьшаем интенсивность стимуляции. Давайте где-то 30 отправим. Маловато. Нам надо получить такую интенсивность, при которой вызванные моторные ответы с руки будут где-то 500-800 микровольт. Маловато. Давайте попробуем так. Видите, я стараюсь держаться перпендикулярно в ближайшей борозде. Заметили, я громко говорила, и в момент моей громкой речи у нас ответы увеличились. Поэтому во время исследований помните, должно быть обязательно тихо, испытуемый должен быть расслаблен. Значит, поставьте, пожалуйста, мизинчик. Все равно у нас ответы, наверное, великоваты. Я сейчас начну еще раз изучать. Чуть-чуть пониже взять интенсивность. Мы ориентировались по интенсивности, и сейчас у нас ответы где-то больше 200, но меньше 800. Сейчас на такой интенсивности мы будем делать грубое картирование для того, чтобы найти горячую точку. Одно из мышц мы выбрали. Причем заметьте, насколько вариативны ответы. Не было ответа совсем, и вдруг ответ выше 5000. У нас очень высокая вариативность ответов, причем заметьте большая разница между мизинцем и большим пальцем.
In the response, and we're registering quite a significant difference between the pinky and the thumb.
Сейчас выбираем мы сделали грубое картирование, и теперь выбираем самые большие ответы для того, чтобы выбрать точку
And now we're going to select the stronger responses so that we choose a hotspot.
Остановим текущую МГ. Вот, это первый канал, это у нас была мышца АПБ.
So this is the R channel.
Ну, мы видим, что на самом деле эта точка явно специфична для... Ну, давайте мы ее и возьмем. В этой программе есть возможность автоматической детерминации моторного порога, то есть то, что мы обычно делаем там, с онлайн-аппликейшн на телефоне, здесь уже зашли.
Now we also have possibility to see a threshold, so that's what we usually do using online
Давайте скажем, что мы
applications.
будем ориентироваться по каналу АПБ и что мы хотим, чтобы у нас ответ был не меньше 30 Все. Теперь он все сделает сам.
That basically take care of itself.
Видите, он меняет. Он сейчас будет менять интенсивность. Вот снизил, да? Было 42, сейчас 38.
So now the intensity will change.
Не позволяет мне стимулировать чаще, чем раз в 1,5 секунды, потому что это может повлиять на ответ. На самом деле я не рекомендую стимулировать чаще, чем раз в 3
Stimulate more frequently than every 1.5 seconds, and I wouldn't recommend to apply
Качество
stimulation
ответа, и заметьте, большая разница между мизинцем и большим пальцем, то есть мы явно стоим на
every
специфичной точке
3
для вопроса.
seconds. So here you see how it works.
Все, нам выдали порог 34. Давайте ему верить.
And we are done. We see a threshold 34.
Оптимальную для порога мы можем то же самое сделать для другой мышцы, но сейчас для упрощения мы будем стимулировать только относительно порога для мышцы adductor pollicis brevis. Будем стимулировать с интенсивностью 110% от 34. Это значит 34 плюс 3, да? Вот, с интенсивностью 37%. Давайте посмотрим, что у нас получится. Мы будем выполнять ТМС-картирование двигательной коры, смотреть на две мышцы.
We will do TMS mapping of the motor cortex.
Заметьте, я стараюсь держать катушку конвекситально в голове. Мне здесь помогает навигационная система, когда стрелка яркая, значит я стою в
So I'm using a navigation system to make
И
sure
я
that
стараюсь
I position
поставить ориентацию перпендикулярно ближайшей
the
девайсу.
device correctly, perpendicular to the hand.
Видно, как меняются ответы в зависимости от положения.
And you see how the responses change depending on the positioning.
Мы почти закончили картирование. У нас по испытуемым
So we are
большая
almost done with the
зона
mapping.
ски, потому что испытуемый занимается спортом. И мы сейчас стараемся завершить картирование так, чтобы у
Our
нас
subject
по
is
краям карты
athletic.
были области, где уже нет ответа. Везде, где у нас, вы видите на коре белые точечки, это области, где были большие визуально-моторные ответы. Желтый поменьше, красный еще поменьше,
On the
а серый
cortex,
это где ответы
these
были
are
меньше
strong
57 микроров.
motor responses. And so the strength of the responses is encoded by color.
Заметьте, когда маленькие ответы, движение руки не видно, ответ все еще есть. То есть ответы, конечно, 50 микровольт, но удивительно не видим.
So the response is 50 microvolts.
И мы посмотрим на карту, которая у нас получилась. Конечно, потом более подробно ее можно анализировать в программах, но здесь можно просто сориентироваться, что у нас получилось. Мы мерили ответы в двух пластах, и вегетимини. Давайте посмотрим вообще, где у нас были ответы больше в одной мышце, где у нас ответы больше в другой мышце. Вот смотрите, коричневым цветом здесь у нас обозначается мышца, входящий мизинец. То есть тут ответы были, где коричневые, ответы были больше в мышце мизинца. Зеленым обозначены те мишени на коре, где были больше ответы с областью. Действительно, мы можем видеть такой небольшой градиент соматотопики, то есть большой палец у нас более латерально, мизинец более медиальный. Давайте посмотрим теперь только, например, для большого пальца, где у нас максимум, где минимум. Вот удивительно, смотрите, у нас максимум ответа на большом пальце, даже не на прецентральной извилине, а на постцентральной. И давайте проделаем то же самое с мизинцем. Здесь мы видим тоже, что у нас максимумы сдвинуты медиальные к верху, и тоже у нас есть самые большие ответы и на области S1, не только на M1. Конечно, дальше, чтобы исследовать, мы должны пригласить другую программу для анализа, что мы обсуждали на лекции.
We can use whatever software is preferable. 1, 1, 1, 2, 3. Can everybody hear me? So we just had an opportunity to watch a video which showed us the use of TMS. Maria Nazarova has joined our workshop. She represents two organizations, High School of Economics and Federal Center for Brain and Neurotechnology of the Federal Medical and Biological Agency. Over to you, Maria. We cannot hear you, Maria. So let's check the screen sharing function. Yes, everything seems to be in order. Over to you, Maria. Thank you very much for your kind introduction. Good morning, everyone. My name is Maria Nazarova. I am a neurologist and a neuroscientist. I'm a researcher. So I do a lot of research into the human locomotion, and I pay special attention to rehabilitating patients after stroke. Today, I will talk about the opportunities that are offered by TMS, and today we will talk about cerebral stroke, which sort of opportunities we have diagnostically, therapeutically, if we have access to TMS. So what is transcranial magnetic stimulation? Well, there are two parts of the first word, trans and cranial. So something goes through the skull. This is a non-invasive method for brain stimulation together with transcranial electric stimulation, which is called micropolarization in Russian literature. But what does TMS give us? It can give us online effects. That's why TMS is used for research of the nervous system, both healthy nervous system and impaired nervous system. It is also used for neuromodulation, which gives us an opportunity to use TMS therapeutically. Let me give you a little bit of a background. So, well, you know, the electric rays were used back in ancient Rome to treat migraines. And up until now, TMS is one of the possible treatments for persistent migraines. When people started looking into electromagnetism back in the 19th century, Giovanni Aldini came up with the notion of living electricity, and then physicists were testing magnetic electricity. TMS, or TMS as we know it today, became widespread back in the 1980s. Here on this picture, you see the first commercial TMS machine. And those of you who worked with a TMS machine, you can see that the TMS machine that was invented back in 1980s looks pretty much like the TMS machines we have today. Well, the only thing that is different is here the transducer is round, but now we have differently shaped transducers. So these methods appeared back in the 80s to stimulate the motor cortex, but now it has much wider applications. We look into motor systems, we apply it in cognitive research and psychiatry, and so on. So what is the difference between the TMS that was used back in the 1980s and the TMS that is used today? As you can see, the machine can be quite similar, but today we can combine TMS with other research modalities. We can combine TMS and EEG. For this, we need special EEG amplifiers, but it is possible. It can even be used in clinical practice, and it is used in clinical practice. And we also have MRI navigation or MRI assisted TMS. I am very sorry that the video, which you saw previously, didn't really have an audio sound, but I'll show you another video how we use MRI navigation and TMS to map everything with the precision of several millimeters. If something in my talk is unclear or you need some more explanation or you have a question, please do use the raise a hand function so you can ask me any questions, give me any feedback using your microphone online.
If there are no questions, let me continue. We use MRI with or without navigation and also in combination with other methods. We can see that the number of publications on TMS, and we're interested in strokes and TMS. It keeps going up. In 2018, we had over 4,000 of them. and we have even more of them today. What is the recommended approach when we use TMS for therapy? In 2020, new recommendations were issued at the level at the A level. We have three reasons to use it. The neuropathic pain, it has some issues, but anyway, we have neuropathic pain, depression, and motor disorders in hands with patients under 6 months. This is what we're going to focus on, what is recommended for strokes. Even there are some issues in terms of improving rehabilitation of post-stroke patients. But let's get back to what we mean by TMS once again. TMS is a method that allows us to use the invasive method to stimulate the surface structures. We cannot go all the way to basal ganglia or to the medium part of the brain. We cannot get there, but we can stimulate the upper layers and the cerebellum. Transcranial means where we put our coil. If we put it on the head, it will be transcranial, or we could put it on the hand, it would be peripheral magnetic stimulation. If you put it on the spinal cord, it would be transspinal stimulation, but we're talking about transcranial stimulation here. And the depth where we are supposed to put is around 20 centimeters under the cortex, where there's a switch between gray and white matter. This is the general principle of how it works. In this coil, there's a copper wire, and it's under current. You induce the magnetic field, and with it in the painless way, it goes through the scalp and induces an electric field. This methodology is painless, as opposed to some of the early methods that were used of transcranial electric stimulation, when it used very high intensity. And it is used for healthy individuals, for patients, and for children. This is what can be used in a variety of areas. All right, what happens after TMS impulse? You get this current in the coil. Some devices show you the current values in amperes. Then a magnetic field is induced, and eventually you get this induced current in the tissue. And it's not just neurons, but all other structures around. But when we talk about the target cells, we mean neurons. These are model works, and of course we believe that we impact layer 3 of cortex, and then transsynaptically we activate the pyramid cells of L5, depending on the position of the coil, depending on how we stimulate. We are going to excite different pools of neurons, and this is the basis of different approaches when they use TMS to assess different pools of neurons in the same area. Is everything clear at the moment? Are there any questions at this point? If you do have them, you can write them in the chat. About positive effect, we're going to talk later. This is not a recommended approach at the moment. It doesn't mean that it doesn't work. There was a large randomized study. I'll tell you why it has been removed from the recommendations. As I mentioned, the cells for TMS, it's level 3, and transsynaptically level 5. The key idea here is that TMS excites pyramidal cells in the transsynaptic way. As for the way or whether we hit it accurately, we stimulate a rather broad area, but the maximum of the induced electric field will be located at the level of the cortex, which is a few cubic millimeters large. We use this method to get some local effects. The most obvious use of TMS to get local effect is, of course, mapping of the cortex, which is used for scientific purposes, which is a routine during some surgeries as pre-surgery functional mapping of the brain. It's information for the neurosurgeon before the operation. What does this locality of the induced field depend on? It's because it depends on the shape of the coil and how far we do it. The simplest placebo is to remove the coil further from the head, and you won't get anything on the brain, and the orientation of the coil form, where it is, the distance from the head, and how you move it. It's about the shape and the distance and location of the coil. What can we do using TMS in the broad sense? We can get offline effects that I was talking about, using it for neuromodulation, and we can get online effects. There's supposed to be an animation in this part of the slide about online effects to study the state of the brain at the moment. These are subdivided into online, offline TMS approaches. For online, we can quantify something, measure some property of the brain. The simplest thing that we can do, we stimulate the motor cortex, we get response with muscles, and we can measure how big it was and look at corticospinal excitement, and we can interfere it with the current process, and this is the foundation of the methods that are called, this really nasty words, virtual damage. If we have current neuronal process, for example, image recognition, we understand more or less where it's going on, how it's going on in the visual cortex, and the data about evoked potentials. We can apply TMS stimulus as powerful impact on the cortex, which interrupts what's going on there at the moment. That's why we can use it for interference with the ongoing task to understand whether this part of the cortex really is part of a certain task. And we can get offline effects. We can activate the facilitating effect and inhibit some of the other areas of the cortex, which is used for therapeutic impact. Before we talk about the actual use of it, let me tell you a few words about safety of this approach. I already mentioned it a bit earlier. TMS is a safe method. It's used for healthy individuals, for epilepsy patients, and even though there are some limitations, also it's used with children, but this is the latest safety recommendation issued 10 years ago. They're going to be revised soon, but the worst case that but about some doubts. If it's really powerful, it can lead to an epileptic seizure. But if we follow the guidelines of no more than so many pulses or so much intensity, then the risk is estimated at 1.4%. For patients with epilepsy, it's a relatively small risk. And in 2012 through 2016, there was a survey of different labs. They had a survey of different labs, including clinical labs that used TMS. And the key point is that the risk, there were only 4 seizures out of the total number of sessions. And the key point was that and the high frequency stimulation was no more likely to cause seizures than low frequency and single paired pulse TMS. If we follow main safety recommendations, it doesn't matter whether you use low frequency or high frequency option in terms of safety. Now about strokes, if you have any questions, I'll be glad to get them. If something is not clear, raise your hand and then your mic will be on. What can we do in terms of stroke? There are some diagnostics capabilities. This is an illustration of what I was talking about. If we stimulate the motor cortex, we get to the pyramid cells of L5, where we get our main pathway of voluntary movements, and then we can activate neurons that give us axons for this pathway, and we get a situation that if you have a short TMS, even in that video, even without sound, you could see that the volunteer had some involuntary subconscious movements that was stimulated by TMS. When we measure it using the surface myography signal, it's evoked motor feedback, and we measure it from peak to peak. There are other parameters that we can estimate the number of phases and so on. These are the details, and with the presence of this evoked motor feedback, it means that functionally your corticospinal pathway is intact. What can we do using TMS? What else? We can stimulate with 2 stimuli, depending on how these stimuli are different from one another in terms of their intensity in the time gap between them. We can get either the reduction of evoked responses or the increase of evoked motor responses, and we will show you how it looks like. It's inhibition or facilitation phenomena. For example, for this phenomenon, short interval cortical inhibition, when 2 stimuli follow one another with very little break of or gap of 2 milliseconds, and one is below, another one is above the threshold, and we get the reduction of response. Let me say immediately about this threshold. TMS of the motor cortex, there we use the notion of calm or active threshold. It's such intensity of stimulation when we talk about calm threshold, where you begin to see the evoked motor response from the muscle, when you begin to register something in your myogram. if we stimulate with less intensity, it does not mean that we do nothing. It simply means that we lack intensity to activate pyramid cells. If we provide stimulus under the threshold and then above the threshold, it still gives us effect. That's why most therapeutic protocols use values below the threshold. It does not mean that these thresholds are, it doesn't mean that we have no impact on the brain. It simply means that it's under what is necessary to activate pyramid cells. All right, I hope, colleagues, this part is clear. If you get any questions, use chat for that. Because sometimes I might miss something in the chat. This was the stimulation with two stimuli in the same spot. We can also use TMS to stimulate several locations with two different coils. We can apply one stimulus one place location and another one at another. It's used in a clinical practice. This is widely used for research. We have one conditioning stimulus and another testing stimulus. And this is probably the best way to look at the connectivity between regions, not just through the correlation that we can see using EEG or functional MRI, or we can look at causal relations between these areas. And also we can use with stroke, which is widely used for functional mapping of the brain before surgery. This is TMS mapping of your cortex. This is a homunculus illustration from Penfold, and it's been discussed many times before. It's more or less a metaphor. It's not all that realistic, but this is what was available for invasive approach in the past. But now with TMS, it's also available. We can, this is our brain here. This is our median sulcus and some of the gyri shown here. And we see the responses when we install our electrode and when we did the mapping, which was also in the original video in the beginning. And here, this is the part for another muscle that is dealing with the pinky. And so this is the map of one muscle. It's really large. There's a significant overlap for different muscles here, and a map for another muscle. And these are also different days. We can assess the plasticity of the cortex during the rehabilitation or training. All right, are there any questions at the moment? If there are any questions, do ask them, of course.
Well, let's go on. That is something which I mentioned before. We can assess cortical reorganization following a stroke using the TMS modality. So let's talk a little bit about neuromodulation. What can we do if we want to change something using TMS? We can use different protocols. For instance, we supply not one or two stimuli, but rather a lot of stimuli using a rhythmic sequence. This approach is called the rhythmic TMS or RTMS. And there are a lot of approaches like this. There are two classic RTMS approaches. One is low frequency stimulation. From low frequency stimulation is from 1.5 to 2 or 3 hertz. And high frequency stimulation, when we're talking about high frequency, we're usually talking about stimulation from 5 to 20 hertz. There are also a lot of burst TMS, for instance, TBS, constant theta burst stimulation, or ITBS, which is intermittent theta burst stimulation. These protocols have been adapted from animal studies. We used to think quite for a long time that they're activating protocols and inhibiting protocols. We used to believe that so when we apply 1 hertz to the visual cortex, we diminish the activity of the visual cortex. If we apply, let's say, 10 hertz to the visual cortex, we increase the activity of the visual cortex. But right now we know this to be not entirely true. These results are different between different subjects, even between healthy subjects, let alone patients after stroke. I already mentioned the new guidelines which were published this year. These are evidence-based guidelines. You see a huge list of experts here who took part in the development of the guidelines. But these are guidelines issued by European experts. What's important about these guidelines is that evidence level A is, or rather incorporates a lot of studies, but it doesn't really mean that it will directly translate into giving us a substantial clinical effect. Oh, I got a question. And somebody is asking, why have you selected theta? Well, you know, when we're talking about theta bursts, that is something that we learned from Taiwanese researchers who took one of the animal protocols, which used theta burst stimulation. So we took the animal model stimulation and adapted it to humans. It turned out that so for some human subjects, theta bursts do work, but for others, they do not. There are certain advantages to the theta burst protocol. If we talk about these standard protocols of 1 hertz or 10 hertz, these are very time-consuming protocols that require from 20 to 30 minutes. Therefore, everybody was looking for faster protocols, and that's why we ended up using theta bursts, because they only take up, let's say, about 4 minutes. If I haven't managed to answer your question, please let me know. What about the angle of tilting? Yes, it is very important. That's why we do use MRI assisted navigation, because the area where an electrical field will be reduced is, of course, regulated by the angle. The next question is that, so do we only stimulate the motor cortex? Well, of course not. We stimulate different cortical areas. I was just talking about the motor cortex because I was talking about post-stroke rehabilitation, but of course we can stimulate different cortical areas. So what is the influence of the 1 Hertz protocol on the medulla oblongata, on the vegetative functions of the medulla oblongata? Well, if we talk about the cerebellum, there are quite a lot of muscles that are located close to the location of the cerebellum. There's also the spinal cord. But when we are stimulating using the TMS modality, we also stimulate the areas that are located more superficially. So we are trying to stimulate the brain, but of course we also stimulate a peripheral nerve. So if you are trying to stimulate speech areas, then you're not only trying to reach the Broca or Wernicke areas, but you're also stimulating some scalp areas. You can stimulate the facial nerve, which will create the tension. So you asked about medulla oblongata. Well, I don't think TMS is not the right modality to stimulate medulla oblongata, but we are studying vegetative functions, but we cannot directly influence the medulla oblongata. But if I didn't manage to answer your questions, then we can talk over the microphone. Okay, let's talk about rhythmic stimulation. Let me just give you, I've already given you a brief overview of the recommendations of the guidelines. The guidelines specify neuropathic pain. So neuropathic pain is one of the indications which has gathered a lot of evidence. Migraines, of course, we can have a lot of approaches here as well. Stroke, that's what I've been talking about. So patients after stroke, especially if the stroke happened less than 6 months ago, then we're using, and patients who have the primary motor cortex inhibition in the unaffected hemisphere. So rhythmic TMS, well, researchers tried to use this protocol for all of the patients, but there was a research that had been published in 2018, research looking into stroke patients 6 months or longer after the stroke. It was a multi-center randomized sham-controlled trial, and this trial said that there is no effect of the transcranial magnetic stimulation for these patients. So we'll talk about why we need to suppress unaffected hemisphere. That is something that we've been looking into. What are the factors that determine whether TMS or non-invasive brain stimulation following a stroke would be helpful? Of course, if you look at it from a global point of view, then we have to see what is the prognosis for the patient. The second part is motor system reorganization model. So what it is that we're looking for, what do we want to make the unaffected hemisphere more active? Do you want to suppress it? How are we going to reprogram interaction between the different parts of the cortex or non-cortical areas? And the third factor is the effectiveness of our TMS for individuals, because even in healthy subjects, the effects of our TMS could be quite different. And all of these come down to the effectiveness of neuromodeling TMS in patients after stroke. So let's talk about potential recovery of these patients. The most important thing here is the factor that hasn't really been studied in depth, and this factor is the intactness of the corticospinal tract. There was a publication that we published in the Stroke Journal, and in this publication, we analyzed patients in the chronic period with different degrees of paresis. If we look at the corticospinal tract in the internal capsule, then we can say that most severely affected patients in the group 3, are very different from moderately severe and mildly severe patients. Basically, patients for whom the hope of recovery is higher. So it all comes down to the intactness of the spinal cortical connection. We have to look at the intactness of the inner capsule. You see these fractional anisotropy profiles in the corticospinal tract, so that I'm pointing to. You see the numbers for patients for whom the prognosis is good, intermediate, and poor. And you see for these patients, everything comes down to the level of the inner capsule. I see that I have questions, maybe not. No, there are no questions. So if we're talking about fractional anisotropy, it is the role of this fractional anisotropy is a bit less in the area of the cerebrum peduncle. What famous indications exist in the clinical practice? Well, first of all, we're talking about acute stroke. So usually after an acute stroke, during days 3 to 7, we can use TMS. A new paper has been published recently that says that TMS can be used during surgery. For instance, if an artery bursts during the acute period, we can look at the corticospinal tract, and the presence of responses is an important criteria for us to establish whether we've managed to recover this brain function. So we were talking about the first point, evoked motor responses and corticospinal tract on MRI. We were talking about it in more general terms, whether the brain function can or cannot be recovered. But there is another important consideration. We cannot, of course, influence the intactness of the corticospinal tract, but we can do something about the organization model. There are two models of recovery. The first model is the interhemispherical competition. The idea is quite simple. The unaffected hemisphere starts to suppress the affected hemisphere, and that plays a very negative role in patient recovery. That's what all of this stroke neuromodulation has been based on. So you see the model that we use in patient recovery today, and it is based on this interhemispherical competition. But there is another model which has been extensively looked into by Russian scientists and other international scientists, and this is the so-called replacement model, which says that the unaffected hemisphere compensates for the lost function in the affected hemisphere, and therefore the unaffected hemisphere and its function contributes a lot to patient recovery. The replacement model used to be very popular, but when it comes to neuromodulation, the interhemispherical model became more popular. But we do see that maybe it is not the right approach at this time, and maybe we do need another model. Well, this model very promptly appeared, and this is the bimodal reorganization model. So if we have a good structural reserve here, then we do not really need to reorganize the interhemispherical equilibrium. But if the intrinsic reserve is rather diminished, then we need the input from the unaffected hemisphere. So a lot of the physical therapy approach are based on this principle. For instance, there is an approach to physical therapy when we take, let's say, the unaffected limb and remove it from the experiment, and we concentrate on working with the affected limb. This is the so-called limit-based therapy. There's also a bilateral approach, but it still remains unclear which approach is the most beneficial. So we are looking into using TMS, and we believe that bilateral training sessions are more preferable for severe patients. So we are trying to combine sufficient neuromodulation and the activation of the unaffected hemisphere. So how do you administer TMS when you have bilateral damage to the corticospinal tract? Well, if we're talking about the interhemispherical competition, well, that is not something that we can do when we have bilateral damage to the corticospinal tract. But there have been a lot of papers, and we're all looking forward to seeing the results of a large randomized clinical trial that is currently underway. But all these papers say that TMS can be beneficial to diminish spasticity in patients with multiple sclerosis. If we're talking about stroke, especially about bilateral damage, I have to say that we do not have one preferred modality. What we can use TMS for now is to decrease the activity of one area and to increase the activity in another.
If we talk about balance between inhibition and excitement, this is from our work the threshold of getting the response, TMS response in the intact hemisphere from mild, medium, and severe cases is pretty much the same. There's no significant change in the corticospinal excitement level. It is not there, and when there's this lesioned or damaged hemisphere, there's this correlation, and this threshold is about pre-morbid level. If we do it on us, we will all have different thresholds depending on the peculiar features of our brain and even the thickness of your skull. How you need to raise the efficiency, intensity for that field to reach the brain through the skull bone. And the key point is that with the stroke, it's recommended that the severe patients compared with those who have restored nicely, they have damage to the motor part of corpus callosum, and how to apply this inhibition from the other hemisphere is not clear. If your corpus callosum is damaged, then there's this clear correlation. You need the structural preservation of some structure in the corpus callosum and cortex. If this is a severe case, then there will be broken links and connections between two hemispheres, even in the secondary manner. All right, let's see if we have any more questions. I can't see anything in the chat. Let's see if there's anything left. About the targets, what other targets you can use with stroke? We talk about motor system and everything that comes to mind. We checked everything. These are the main ones. This is the insult in stroke area, and inhibition of the healthy hemisphere, and the RM1, rather vague area activating of the damaged hemisphere, and everything that has to do with the motor system, additional the motor ventricle, dorsal areas, and additional somatosensoric cortex, and of course cerebellum. We study all this, and it's all quite interesting, but it's all at the level of research. Let me check the chat once again. Louisa, please advise me on whether I still have time or not. In terms of our schedule, we still have 16 more minutes. You do still have some time. All right, let's focus on that. You can always see the video afterwards. It shows standard protocols. You can stay and watch them. My first point was about the TMS effects with stroke patients are determined by how well we can restore functions at all. My second point was what kind of model of reorganization we want to use. And my third point is the impact of protocols, or whether 1 Hertz is activating or not, whether 10 Hertz or inhibiting or non-inhibiting, activating or non-activating. Even with healthy subjects, we show different approaches. For example, one is with theta bursts, black respondents, gray non-respondents. And it's about all types of neuromodulation. And when we look at the activating or inhibiting protocols, we expect the increase of evoked motor responses. We had 100, then everything here is above, and everything here is below. And for responders, we have about 40% of them, and that is repeated from study to study. If you turn on 1 hertz, it doesn't mean that you will get inhibiting protocol. It sounds really scary how you can use it at all. And what we believe, and many other researchers believe on that, it's the idea that we need to monitor connectivity in the brain and peculiarities of how it's organized and reorganized with every specific patient. One particular lesion impact the entire connectivity of the brain. And what we're doing is trying to monitor certain current states in the brain. This is an emerging topic at the very beginning of the process. There are no good markers. Some wanted to check phase of power or the algorithm. It works a little better with phase than with power, but it's not an ideal marker. This is what the global community is working on. And if you are working in the adjacent field, it would be great to start some kind of cooperation here. This is the hottest topic, trying to capture those specific states of the current functional state. And it's not only about EEG, this is just an example. We do it with EMG and with anything that measures current biological activity, heart and anything else, catching some biological states. How our brain is going to respond, the reactivity of the system is determined by its dynamics. This is what we do as well. This is this idea of critical state. Depending on the state of the system, there are different opportunities to transfer information. If the probability of signal going on is 50-50, then after certain excitement, the entire system is going to be excited. And if the probability of signal transfer is 1/1000th, then everything will be inhibited. But if there's a certain intermediate state, then there's an opportunity to transfer information in the system. And there are attempts to find some EEG markers. In particular, we use autocorrelations in the magnetic or electric signal, how this signal correlates with its self. And this is one of the parameters that we try to use to predict the individual reactivity of the system, whether this brain, in principle, is able to respond to an impact. As for the current neuronal activity, as I said, this is the most active study. I'm not going into details there, but what really works now, and this phase of neuralism, if we talk about this, and desynchronization of beta, and we try to find some markers in EEG to stimulate at a certain point what's going on and get better effects. And for stroke, it's really connected with BCI technologies. Well, imagine the movement when you capture a certain brain state. This is a better desynchronization, for example, and at this point you apply the stimulation, and there's an idea here to move from non-invasive approaches to invasive methods for patients with severe paresis and to use individual electrodes to stimulate patients at home. What do we expect from TMS with the stroke? What we discussed here is to stop doing the same thing for everyone. Currently, the approach is to inhibit the intact hemispheres for everyone, and others are trying to look at the structural reserve, functional reserve of the damaged hemisphere, depending on whether it is intact or not, or then you have to think about whether it's activation or inhibition. And you have placebo-controlled, you need to have placebo-controlled studies. It's useless without placebo. And I hardly ever mentioned this part about TMS and EEG. TMS and EEG markers in psychiatry are quite popular in schizophrenia and other disorders, and activity-dependent stimulation is the way they try to take to avoid this variability of effects that keeps us quite limited in how we can use this stimulation, because when you have 15 to 20 patients, it's one thing. When you try to assess it in a small group, you lose the effects. And what I failed to mention, even now, for scientific purposes, we can use multi-channel TMS devices when you have lots of coils, and using them, you can stimulate here and then here with gaps of milliseconds. And this is a new area of TMS studies. I'd like to thank you for your attention.